students, myself Tanmoy Dotto, Assistant Professor, Department of Chemistry, JS College of Engineering, welcome you all in my second lecture of Stereochemistry. In the previous class we discussed about the isomer. Okay, the isomer is a very important topic or important concept for the stereochemistry. Different types of isomer we already discussed. So today we'll discuss about the most important topic of the stereochemistry, and this is called the optical activity. So you have to know about the optical activity and the plane polarized light. Okay, so we will discuss today optical activity and the plane polarized light. Then we'll discuss about the what is the chiral center. Okay, so what is the chiral center? We will discuss about the chiral center and corresponding to asymmetric center. What is the asymmetric center? What is the chiral center? We will discuss about these things. Then we will discuss about the most important things, that there are what is the small d and what is the small l. That means there are dextrovatory, there are plus direction rotation and minus direction rotation. We will discuss about these things, that how we can understand or what is the role of this dextro and liberatory, the plus or minus, with the plus and with the minus direction. Okay, there are two kinds of direction of rotation is possible for the sample. We will discuss these things also. And then most important things of this chapter. Okay, today I will show you that what is the Fischer projection, what is the Fischer projection, and what is the flying wedge projection. What is the flying wedge projection? So these two are very important thing of the or for the stereochemistry. Okay, you have to keep in mind, you have to properly understand that how we can write down the Fischer projection and how we can write down the flying wedge projection. Okay, because the Fischer and flying wedge, these two are totally, we can change from each other, we can jump from one to another. By there's some rules also. By following that rule, we can write down Fischer projection to flying wedge projection, or flying wedge projection to Fischer projection. So this concept is very important for the stereochemistry. So we will discuss all these things, okay, in today's class. So without further delay, let's start the class. Okay, so first of all, what is the optical activity? Okay, so how we can define the optical activity? So optical activity is the ability of a chiral molecule to rotate the plane of plane polarized light using a polarimeter. Now there is some question arise, I think. So first of all, here it is written that optical activity is the ability of a chiral molecule. So what is the chiral molecule? So obviously we have to know what is the chiral molecule. Second, to rotate the plane of plane polarized light. What is the plane polarized light? Maybe it is the next question arise in your mind. So first of all, we'll define or we'll discuss about the what is the plane polarized light. Okay, so look here, plane polarized light means light has been passed through a nickel prism. If any continuous light has been passed through a nickel prism or other polarizing medium, then so that all the vibration are in the same plane. Okay, so if you look carefully the picture, generally for any light there are so many vibrational planes are there. Okay, so look here, it is one vibrational plane. Okay, that for non-polarized light, the vibrational planes are in different direction. Okay, there are so many direction, and each and every direction actually look there the vibrational planes exist. But when this light pass through a nickel prism, then what happen? When this light pass through a nickel prism, then what happen? Then this plane polarized light, it is showing that all the vibrational plane will be in the same direction. Okay, this is called the polarized light. Okay, so in case of your non-polarized light, the vibrational planes are in the different direction, but in case of polarized light, all the vibrational planes look, they are the same direction. So you have to keep in mind this point, because this is very important to understand the rotational plane of the light. before rotation, understand the rotational plane of the light, you have to understand what is the plane polarized light, because without the polarized light it is not possible to rotate the plane, because if all the vibrational all the vibrational planes are not in the same direction, then how it is possible to rotate the planes? Okay, if it is in the different direction, then it is not possible to rotate the plane of the plane polarized light. Okay, so now look here that this is the polarimeter. Okay, in the second line of the definition, okay, just look the second line here, it is written one line that measured using polarimeter. Actually, if there is any kind of a rotation of the plane polarized light, how we can understand if there is rotation or not? We can understand by the polarimeter. Actually, polarimeter tells us either there any kind of rotation occur or not for the light. Okay, so that's why here look here, this is the polarimeter. The polarimeter, what is the role of the polarimeter? Polarimeter as instrument used to measure the optical activity. It is the instrument to measure optical activity of the light. Okay, so optical activity of the sample. Okay, so a sample polarimeter, a simple polarimeter of a light source, polarizing lens, sample tube and analyzing lens. So these are the instruments which are used here in the polarimeter. So this is not very much important here for our point of view, for the stereochemistry point of view, but you have to understand that look there, that this is a light source. Okay, so these light source are what I told you, that light source generally it contain so many vibrational planes are there, but when it passed through the polarizer, what I told you in the previous slide, that nickel prism generally it is used as a polarizer. When it is used as a polarizer, then what happened? Look, there only one plane. This is all the planes are, and there are they're removing by the one plane. Okay, so when one plane, then this plane will when it passed through the polarimeter or the pass through the sample, then what happened? Either it can rotate clockwise or it can rotate to the anti-clockwise. So what will be the rotation? This will be measured by the polarimeter. Okay, so in this case, in this example, look, this is the rotation occur in the clockwise direction. Okay, so that's why look, it is the single, it is the 90-degree angle, but look here, it is the slightly rotate in the right hand side or the clockwise direction. Okay, so that means this sample is optically active. Now this sample is called optically, it is optically active. Why optically active? Optically active because it rotates the plane of the plane polarized light. If any sample is able to rotate the plane of plane polarized light, this is the sample is called optically active sample. Okay, so this sample is called optically active sample. Okay, now so now look here that in case of there is a chance of the rotation of the plane in the two direction. Okay, either what I told you, either clockwise or the anti-clockwise, depending on this rotation. Look, there are two types of things. One will be dextrorotary, this is very important, or it is the plus, or another is the levorotary or levorotary. This is generally taken as the minus. Okay, so an optically active compound that rotate the plane of plane polarized light in a clockwise direction. Okay, so this dextrorotary means it is the plus direction, it is the clockwise. Okay, this is the clockwise direction. If the plane of the plane polarized light any sample rotate in the clockwise direction, then it is called the dextrorotary. Okay, but if it is in opposite direction for any sample, if it rotate the plane of the plane polarized light in the negative side, okay, or anti-clockwise direction or counter-clockwise direction or anti-clockwise direction, then it is called the levorotary. Okay, so levorotary, or it is negative, or it is for the anti-clockwise direction. Okay, so now look here that here there is one important term that here it is do not confuse with the one thing is very important here, that here this D, okay, what I told you, this D, do not confuse with this D, because though here it is written here dextro capital D it starts with, but you have to take the small d here and plus sign here, or for levorotary either small l or the negative sign. So these two things is very important, you have to keep in mind. So that's why I told you that don't use here capital D, okay, capital D and small capital D and capital L, that will be used for another purpose. So here you have to use the small l or small d or plus or minus sign for the dextrorotary or levorotary. Okay, so now there are so here it is written also, do not confuse with capital L. Okay, do not confuse with the capital L, because here you have to use the small l or the small d. Now there are two examples are there. Okay, so the angle of rotation of plane polarized light by an optically active substance is proportional to the number of atoms in the path of the light. Okay, so look here, there are two compounds, both are the lactic acid. Okay, both are the lactic acid, but what is the difference between these two compounds? Only the difference, that's why it is the optically active compound. The left hand side, this one, it is the plus or D, that means it rotate the direction of the light in the clockwise direction, it rotate the clockwise direction, and another one it rotate the light in the anti-clockwise direction. So one rotate the plane of the plane polarized light in the clockwise direction, another rotate the plane in the anti-clockwise direction. So this is the difference between these two compounds, though the compound looks same, but there is some kinds of difference there in between these two compounds. That's why they show the difference in the rotation of the plane polarized light. Okay, so both are the lactic acid, but both are the lactic acid, but they are not in the same way they rotate the plane polarized light. Okay, now come to the next topic, that a specific rotation, that means this is that how much rotation is possible. There may be some kinds of things are included here in this way. We can actually take the value, the angle of rotation of plane polarized light. If it is 1 gram per centimeter, then the equation is alpha d, that equals to alpha into L by d, where alpha is the observed rotation, L is the length, path length actually, that which container sample exists, D is the concentration. Okay, and alpha d, there are some values are there. Okay, that is not so much important for your syllabus. Okay, so you can keep in mind for the knowledge purpose, for the concept purpose, but this is for your according to syllabus, this is not so much important. Now come to the most important part of the stereochemistry. Okay, so come to the most important topic of the stereochemistry, that is the asymmetric center. What is the asymmetric center? Okay, or how we can define the asymmetric center. Okay, so if you take the example of asymmetric center, then another term that is almost parallel with the asymmetric center, there is the chiral molecule. Okay, there is a chiral molecule. Generally, the molecules containing an asymmetric center, this is called the chiral molecule. That means look here, that chiral molecule and the asymmetric center, they are very much interrelated with each other. That means one molecule will be chiral when it contains one asymmetric center. Now what is the asymmetric center? Generally asymmetric center means the bonded atoms, so 4 different groups will be there. Okay, so if you generally we consider one tetrahedral molecule, or generally we take the carbon atom which have the valency 4 and which have the 4 bonded atoms are present, and there we consider that there to be the asymmetric compound, okay, or the asymmetric carbon center. What is the required, what is the necessary condition? The necessary condition should be there that there four attached atoms will be different. If the four attached atoms are different, then only it is possible to get the asymmetric center. That means here this compound, specifically this compound, is the optically active compound because their four different groups are attached with the chiral with the carbon center. Okay, so look here, this is the real example that one group is CH3, another group is CHH, another group is OH, another group is H. So we can call this chiral center, this carbon center is called the asymmetric. Okay, this is the asymmetric center, and this compound is called actually chiral compound. Okay, this compound is called actually chiral compound, and this center also called it is the chiral center. This center is also called it is the chiral center. So there are so many terms which I told you. First of all, asymmetric carbon, which have the four different groups attached with the carbon. This is called the asymmetric carbon. Then the compound may be chiral or the center may be chiral. Okay, if it is an asymmetric carbon, the center may be chiral center. Then look here, there are some examples of the chiral center. So it is the example where star marks. Okay, you have to keep in mind in stereochemistry where it is mentioned in the star marks on which carbon. So this carbon will be the chiral carbon. Okay, chiral means it is the asymmetric carbon. So look here, here it is a star mark. That means this carbon is the asymmetric carbon because look here, one group is here, one group is here. Look here. This is this side one group, this side one group. These are two defined groups are there. In the lower side OH and one is the hydrogen. So these are the four different groups are there. Okay, so that's why if four different groups attached with the carbon, then obviously it will be the asymmetric carbon or the chiral carbon. Then all the examples are like that. It is the one group is the CH3, another group is the CH2 CH3, another group is the Br, and another group is the CH. Okay, so these all the centers are in this way. These all the centers are the chiral center, or this is called the chiral carbon also. Okay, so you have to keep in mind that what is the chiral carbon, what is the asymmetric center, what is the chiral molecule. Okay. Okay, so chiral objects, there are some examples of the chiral objects and very interesting way. In a very interesting way, look here. That if any chiral compounds in from our daily life experience. Okay, so these are the chiral objects actually, how we can understand. So look here, it is the right hand, but all of you I think observe this fact. If your right hand, it seems like the left hand in front of your mirror. Okay, so if there is any chance of like this, then the compound will be chiral compound. Okay, if it in the mirror, if it is not superimposable actually. Superimposable means if right hand become right hand, then it will be superimposable. Okay, so if right hand become left hand in the mirror, then it will not be superimposable. Okay, so then this is called the chiral object. Okay. Okay, these are your R also. Okay, like these also, these all are the examples of the chiral. But a chiral object like a chair, there is no difference in the chair. There is a spoon actually, then glass. These all are the examples of the achiral. Okay, achiral objects. So achiral objects, it looks like similar. Now in the scientific term, what is the meaning of similar? Similar means here it is a superimposable. Okay, if you keep the center over by on the other center on the other object, then this is called actually a chiral molecule. Okay, so now chiral objects are here what I told you, that chiral objects are with left-handed and right-handed forms. Okay, achiral molecules, the objects that have superimposable mirror image. Okay, superimposable mirror image, that means achiral means what I told you, that the mirror image of the particular compound that will be superimposed, that will be parallel or it will be overlap with the other compounds, that are called the achiral objects. Okay, non-superimposable mirror image, a mirror image that is not the same. Okay, what I told you, that non-superimposable mirror, that is very important term also for your stereochemistry, because non-superimposable mirror image means this is actually chiral. Okay, non-superimposable mirror image means this is the chiral, and achiral means it will be superimposable mirror image. That means which have the mirror image which will be overlap with each other. This will call the non-superimposable mirror image. Okay, and this by this way we can differentiate these things actually chiral, achiral, depending on the mirror image. But you have to keep in mind what is the meaning of the non non-superimposable mirror image. Non-superimposable mirror image is the another indication of the chiral molecule, because all the chiral molecules that generally that has the non-superimposable mirror image relationship. Okay, so that's why you have to keep in mind that which will be the non-superimposable mirror image and which will be the superimposable mirror image. Okay, now come to the chiral centers. Okay, so what are the chiral centers? Okay, so chiral center means a point in a molecule where 4 different groups or atoms are attached to the carbon is called chiral center. I already told you it looks like asymmetric center also, but here we will explain in details that what is the chiral center. If 2 groups are same, then there is only one way. Okay, if 2 groups are the same, then there is only one way. A chiral molecule usually has at least one chiral center, what I told you. Okay, at least one chiral center. Okay, so these are the example. Okay, so this is the example, means this carbon is actually bonded to the 4 groups. This is a chiral carbon. Okay, this is the chiral carbon actually. This is the chiral carbon, and now in the second case actually these are the different examples of the chiral carbon. Okay, stereogenic center is the different things which I'll discuss later. Here it is not required at this moment. Okay, so now okay, these all are the these are different projection. Actually I will discuss in details what are the different types of projection. This is actually called flying wedge projection. Okay, up down manner, this is called actually flying wedge. That all are the flying wedge projection. What is the flying wedge projection? I will show you. Actually projection means how we can represent one compound on the plane. Okay, there are different ways by which we can represent one compound in the space. Okay, so that's why this is generally this is the examples of the chiral. Here it is written that level of the stereogenic centers each molecule and decide if it is chiral or not. So if there is different groups are there, then it is that all are the chiral carbons are there. Okay, now what is the meaning of configuration? Actually this is very important. Configuration means it is the arrangement of the atoms that characterize a particular stereoisomer called its configuration. Okay, that actually characterizes a particular stereoisomer, by which it is possible to characterize a particular stereoisomer. We call this is the actually configuration. Okay, so now the following methods are used to assign the configuration. Okay, so absolute configuration. So one type of configuration is RS. This is called RS nomenclature. This is very important. You have to understand properly. Okay, so RS nomenclature. And the second thing is that relative configuration, that is called D and L. I told you that when at first I write down there D, capital D, but then I told you that capital D and capital L, that indicates some different things actually, because the rotation indicates small d and small l, dextro and levo. So that's why here I will discuss that what is the capital L and capital D. But before that you have to know what is the RS nomenclature, or how we can discuss that what is the R nomenclature and what is the S nomenclature. Okay, so first of all, what is the Fischer projection? Okay, I told you that there are different kinds of projections also there. Okay, so one is the Fischer, and there is the flying wedge. Okay, then there is the Newman, then there is the Sohos. There are different kinds of projections are there. Okay, I'll show you one by one projection, each and every projection. So first of all, in the Fischer projection, look here that Fischer projection, the first system for doing this was developed by the Fischer. Okay, name of the scientist. Fischer first developed a method of drawing carbohydrates in 2 dimensions. Okay, carbohydrates are very long. There are so many atoms present in the carbohydrate. Okay, they are very big structure. So, but at first time Fischer was established that how we can write down in 2 dimension figure, and the so-called this is a Fischer projection. And Fischer and the Rosanov then devised a notion for the designing of the configuration of the D and L. This is also important. I will show you that they also developed some kinds of things which we can also assign by the D or the L. Okay. So first of all, look here that what is the D and what is the L. These are the simple things. Then I will discuss what is the R and S. Okay. So D means, here look here, it is a capital D. Okay, keep in mind the previous was small d as small. So capital D. So first of all, Fischer projection. I will show you that how we can write down Fischer projection, flying wedge projection, etc., etc. Then I will show you that what is the D and what is the L, what is the nomenclature R, S, etc., etc., all these things. Okay, so first look how we can write down the Fischer projection. Okay, so if we consider the Fischer projection, then look here. For example, we are taking very common example that this is the C, then OH, then CH3, then F, then Cl. That means this is the central carbon is the C, and with this carbon there are 4 groups are attached, and obviously I told you that for chiral carbon there are 4 different groups should be there. So hence there are 4 different groups are there. One is the wedge, CH3, F and Cl. Then how we can draw the Fischer projection? Okay, so Fischer projection, this will be 2-dimension figure. You can write down here in this way. In the middle, when it cross each other, that indicate that in the middle portion there will be carbon. Okay, and in the upper portion there will be one group, the CH3. It is arbitrary. Okay, I'm writing it, but there will be some particular way by which you have to write down Cl. So actually this is the way of representation of the Fischer projection. Okay, so just take this in this way, that in the middle there is the carbon. Okay, here it is the carbon, and in the fourth side there are 4 different groups are attached with this carbon. Okay, so that is the Fischer projection, and the main thing of the Fischer projection is that you have to represent the Fischer projection in this way, that there will be some 4 groups are attached in this way. There may be here I am taking here small lines are there. Okay, so then for example you are taking that it is the OH, it is the, for example, it may be C2H5, it may be C2H5, it may be CH3, it may be CH3, and it may be F. So this is the a particular way, particular pattern by which we can show the Fischer projection. Okay, and this is very important, which you have to keep in mind, that Fischer projection is the 2-dimension. By this way we can represent the Fischer projection, and there each and everything have some meaning, but Fischer projection has some facility also. Okay, facility means I will show you what is the facility. Facility is that that for example you are taking this compound, like it is the F, it is the Cl, it is the bromine, and it is the iodine. Okay, for example. Okay, so in the middle there is carbon. So there are 2 ways by which you can interchange the position of the group. What are the ways? You have to complete one triangle. Okay, you have to complete one triangle by which you can interchange the group position. Actually, groups means group position. For example, you can complete the triangle in this way, that iodine will be here, chlorine will go here, and fluorine will come here. So this triangle you have to complete it. That means the structure become now after the conversion, that iodine at first come here, chlorine will come here, and fluorine will come here, and then you can write down the Br. This is possible for each and every way. Okay, this is not necessarily that it will be applicable only for this way. You can also interchange this compound in this way also. So anyhow you have to change the position of the 3 atoms. Okay, you have to change the position of the 3 atoms, then only it is possible to represent the compound, to represent the similar compound. Okay, because these 2 compounds are similar. If you follow this process, then Fischer projection will not be hampered. This is actually rule of the Fischer, that you can complete a triangle and you can interchange the groups, so many groups by this way. Then we'll get the similar types of structure. Otherwise, it will be changed. Okay, otherwise it will not be the same with respect to the previous one. So you have to follow these things. You have to complete the triangle in anyhow. Then come to the point. So now I will show you that how you can show Fischer projection to flying wedge projection. Okay, this is very important, you have to know. So I will show you different projection. This is the flying wedge or wedge dash maybe. So this is called the flying wedge projection. Okay, this is actually 3-dimension representation. Okay, not like only 2-dimension representation. So how we can convert the first of all how it looks like. Okay, so then I will show you that how we can convert. So it looks like there are 4 groups of the carbon. So it looks like in this way. There are the 2 bonds, then another 2 bonds, one will be up and another will be down. Okay, this looks like 3-dimensional figure. These 2 on the plane, these 2, it is no problem on the plane, but another one, this one, okay, this one is the bold line or the thick line. This is the above the plane. Okay, it is the above the plane, and another dotted line will be, it is the below the plane. Okay, you have to imagine this is the structure, that in this way we can show the flying wedge projection. Okay, so in the flying wedge projection, in the middle portion also there in the carbon exists. Okay, here carbon exists and there are 4 groups are attached in this way. But what is the difference between Fischer and the flying wedge? In the Fischer look here, in the Fischer projection, there in the Fischer projection, look there are the 4 groups are on the line. Okay, the 4 groups are on the line, but in case of flying wedge, look here, this is not, 4 groups are not on the plane, 2 groups are plane, these 2 groups are plane actually, another 2 groups are, one will be above the plane and another will be below the plane. Okay, so this we have to keep in mind. This is the difference between Fischer and the flying wedge. Now I will show you that how to convert how it is possible to convert for you that from Fischer projection to flying wedge projection. Okay, so we are taking one example, one common example, that this is the structure of the Fischer projection, like it is the Cl, it is the Br, it is the F, and it is the I. Now you want to write down this compound to the flying wedge projection. Now there are 2 ways by which you can write down the formula in the flying wedge projection. So first of all, when you write down the flying wedge projection, just make this line. Okay, make this line. Okay, very simply just draw the line. Now if the line is the right hand side, if it bends the right hand side, because with respect to this line, look right hand side. So if you draw the line in this way, right hand side, then just draw in this way that it is the upside, it is the upside. Okay, it is the upside, another will be downside, dot line will be downside. Then you have to place the 4 groups here. Okay, simply. So if the line, when you are drawing, if you can draw this line also in this way, in the left side also, then the position of the groups will be different. But here, since you are writing here in the right hand side, just you have to place the groups in this manner, that in which direction you bend the line. Just try to listen, try to understand. In which direction you bend the line, the upside group will be there. Okay, that means if you bend the line, in the right hand side, the groups which exist in the right hand side, that means this group will go to the up position. Is it clear? You write them when you convert the Fischer to flying wedge. When you convert the Fischer to flying wedge, then what you are doing, you have to write down in up and down form. Then the question arises that which group will go to the upside, which group will go to the downside, etc., etc. Because this line, this line actually this line. Okay, this line actually this line. That means here it is the Cl and here it is the F. There is no question about this. Okay, so just make this, it is the Cl and it is the F. There is no question. Okay, this straight line actually you write down here in the bend form. Okay, there is no question. But another 2 groups, Br and I, which group will go to which side? So just keep in mind when you are drawing that in which side you bend with respect to u. Okay, so it is the right hand side. So right hand side group will be the upper position, that means another will be the below position. Okay, so this fact is very, very important. I will show you another example, then it will be more clear that how you can write down the 4 groups, or it is the Fischer, and it is the flying wedge. Okay, so you have to keep in mind this conversion. This is very, very important. I will show you another example also. For example, this is the CH3. This is the Cl, this is the I, and this is the F. This is the Fischer configuration. Okay, but you have to convert it to the flying wedge. So what I told you, just what is your duty? Your duty is to first draw the this line. Okay, CH3 and I in this way. So I am showing you that suppose you are drawing in this way. you are drawing in this way. Okay, so then first write down that it is the CH3, no problem, it is the CH3 and it is the I, so I will be there. But next question arises that one will be upside, another will be downside. So which will go to the upside, which will go to the downside. So according to the theory, it bent into the left side, isn't it? Okay, previous one was the right side and it bent in the left side. So which group exists in the left side? This group exists in the left side. So left side group will be up position and right side group will be down position. Simple. In which direction you bend the line, the group of that position will be in the up position. In the same way, I'll show you if you want to convert flying wedge to Fischer, then same theory will be applicable but in different opposite direction, okay. So look here, so it is the flying wedge, okay. It is the flying wedge structure. So Cl, Br, CH3 and I. So you have to convert this structure to the Fischer projection. So same way, just opposite direction follow. This is Cl and Br. This is the straight line. So just write down Cl and Br. Okay, no confusion regarding this fact. Now it is in which direction? It is in left side, isn't it? It is in left side. So left side, if it is bent in the left side, so left side group will be the up position, or up position group will be in the left side. So it is the up position group, isn't it? So it will be left side. Left side means it is the CH3. So here it is CH3 and it will be the I. That means if you convert that, if you convert there to there, CL, no problem. That is very the left side. So the group which exists in the left side, it will be the up position. So if it is the left side, it is the left side. So left side group will be the up position. Okay. So that means, okay. So it is right position. Okay. No, it is not right. It is not right actually. Left position group will be upside. So that means, which is the left position? Left position is the left position actually. It is the left position. So here it will be CH3 and it will be the I, because it is in the left, it bent in the left position. So left position group or left side group will be up position. So here it is the left side, so it will be the up position. So if you convert now CLBR, it is left side. So which group exists in the left position? It will be upside, so it will be upside. Another group will be downside. So in this way you can convert Fischer to flying wedge or flying wedge to Fischer. This is very important. You have to practice a lot. You can take any of the structure, then you can easily convert it in the way of the Fischer to flying wedge or flying wedge to Fischer. Okay. So now this is all for today. Okay, in the next class we'll discuss about the next topic of the stereochemistry. So today what we discussed till now, we discussed about the Fischer projection, we discussed about the Fischer projection, we discussed about the flying wedge projection, we discussed about the first of all what is the DL optical activity, plane polarized light, etc. All that things we discussed today. So thanks to all of you for watching my video, for attending the class, and we'll meet you with I'll meet with you in the next class with the next topic of the chapter. Thank you. Goodbye.